Hello, I'm Harlan. I will be talking about a Python DSL we wrote for writing superconducting circuits. This is going to have a pretty different flavor from a lot of the other talks that have already occurred, so I'm glad you stuck around. So first of all, I should set some context. Pretty broadly, historically, we've benefited a lot from Moore and Dennard scaling. And all I mean by that is that for a long time, we could shrink the size of transistors, cram them onto integrated circuits, and clock our programs faster. We could get faster programs clocking them higher. And we didn't really need to worry about power, but it's scaled proportional to area. But we finally made our transistors small enough that we actually need to start thinking about heat dissipation off the chip. So we really should, we still want faster and faster programs, but one way to maybe get around this issue is looking into emerging or alternative technologies. And so one of those is superconducting. So practically superconducting trades on this low-level quantum effect called a Josephson effect, but I'm not going to talk too much about that. Practically, I'm just going to think of these as transient pulses. So the diagram is what I should explain really quickly. Classically, in CMOS with semiconductors, we can think of two wires, and they have this constant voltage piping in the values. So I can always put a multimeter on the wire and say, well, is it high or is it low? And what that means is I can kind of think of my wires as being stateful, and the gates downstream can be stateless. But when I switch to this transient pulse-based system, I have these picosecond long pulses. And so there's no longer this constant voltage draw where I can check what the value of a wire is. I either heard the pulse or I didn't hear it. And that means that wires are kind of stateless now, but the gates downstream need to keep track of when pulses arrived, and now they're kind of stateful entities. So one part is awesome. Now I don't have nearly the same sort of power draw. So that's really good. That's the thing that was problematic. But at the same time, I'm now living in a vastly different computational domain. I have a very unique information encoding. And in fact, in the design space of superconducting, there's a lot of disparate logic schemes for describing these things. A lot of basic blocks and no standardized design rules. And part of that is that what I get is this asynchronous system where timing information becomes extremely important. So, I mean, we've been able to make superconducting circuits for decades. It's kind of like a spectrum from low level to high level. So on the low level, we have this left picture where you might be more of an electrical engineer and you draw the schematic where you're actually placing Josephson junctions places to route them. And that's awesome, it's accurate, but requires a huge amount of accurate and intense labor to make. You would then simulate that, for instance, and that would be the input to something like SPICE, an analog circuit simulator. On the other end of the spectrum, you could abstract the behavior a lot of superconducting gates and think of them just as functional objects, in which case you might come up with something like a finite automaton, like a Mealy machine. And so you could see where you have these sort of cycles of Josephson junctions with they sort of create superconducting loops, which keep track of state. You could actually think of that as being a state in a finite automaton. So the A arrived is the state, and now my edges keep track of, do I propagate a pulse or not? But the problem is that that's not particularly granular. I just made this big point that timing is important. And for instance, what happens if two pulses arrive at the same time? So one is very intensive labor-wise but accurate, and one is easier to work with but not as accurate. And you could imagine using something maybe a little bit more in between. I mean, people have used Verilog to write RSFQ, a certain type of superconducting circuits. But this is a fundamental mismatch, right? We already talked about how the wires are stateless in superconducting. And Verilog sort of assumes you have these latching wires where you can check the data on them. Not to mention, in a superconducting space, right, we want to be able to model lost pulses or dynamic arrival times, stochastic times when those change. So when these programs become larger and larger, it becomes harder to sort of feel that you did something accurate. So our approach is a Python DSL that we will let you use for rapid prototyping superconducting circuits. It can simulate them, and we can integrate it with a model checker to talk about correctness. So just to give you a better picture, in this chart, we have the semiconducting space, sort of has these voltage levels, transistors, gates. We understand it all the way up to the application level. In superconducting, we sort of feel that we really only have the very low-level stuff about fluxons and Josephson junctions. But there's not a standard cell library. There's no standardized design rules, certainly not microarchitectural stuff or even application level. So that's what we've been trying to target with our DSL. So the sort of abstraction we came up with, we called a pulse machine. So effectively, we took that Mealy machine from earlier and we decided to add back in all the information we thought we needed that was missing. So we have a priority for when 2 pulses arrive. We have transition times that can model setup and hold time. We have delays for if a gate needs to propagate a pulse that happens after some amount of time before it appears later in the circuit, and some various other constraints. So what does that look like in our library? We chose Python so that it would be pretty straightforward. This is a synchronous AND gate. And as I just talked about, it kind of looks like a labeled transition system, and so that's how we're going to specify it. We specify the setup and hold time, some other firing delay information, and mainly we just have this transition key value store where you specify states with transitions, sort of source target, and their labels. So it's a transition system, Python DSL. We give you 16 basic cell classes that we've deemed very useful. For instance, again, it's our synchronous AND gate, but there's other things like inverse C elements and things. But it's sort of extensible, so if you feel like you have a better cell or a different one that you want to model, you're very welcome to do that. So what does it look like to program in this? Well, if we look at this min-max pair, which is an element that kind of orders its inputs, we sort of have 2 inputs coming in, and we want to make sure the smaller one comes out on the top wire and the second one comes out on the high wire. So what does that look like? Well, we try to just mimic the block diagram. So on the code on the bottom, we write this as a function, or we imagine it's a function. So the S is a splitter, which sort of just splits 2 wires. So we have a splitter on A, gives us A1 and A2. We start piping that around through the C and the C inverse element and so forth. So this makes it very easy to write larger designs because you can just import them and think of them functionally. And then you're allowed to overwrite the firing delays and things like that as you need. We talked about the microarchitectural level. So a lot of things in superconducting don't really exist yet. So for instance, memory is a little tricky. And so what we did was, well, if we want to mock something up, we want something quick and dirty, we have this idea of a hole. So as long as you respect the input-output behavior of a chunk of your circuit, you can write somewhat arbitrary Python code to get the values that you want. So this is very helpful for making larger designs, as the space of superconducting sort of normalizes around things like memory. So we need to grade this with respect to the industry standard, like I mentioned, SPICE. One thing on the left that we care about, I mean, there's more tables like this in the paper if you want to check them, but on the left we have the industry standard of SPICE. And so if you want to write a gate like the C gate or the inverse C element, it might take you 81 lines of SPICE code, and it could take maybe 3 seconds to simulate. In Pulse, it's 6 lines of code, and it takes vastly less than a minute to simulate, so it's much easier. I want to make sure that I mention, though, that that's not really a problem with SPICE. SPICE is a massive, very useful analog circuit simulator. But for the things that we need, we can get away with a lot less. And so we're able to pare down a lot of the complexity. And then in terms of correctness on the right, like I said, timing analysis is extremely important. So the SPICE timing analysis of a min-max pair is on the top. As you simulate pulses on the A and B wire, you'd expect to see them at the appropriate time on the low and high. And in our visualization, we see that our red pulses match, and so we have accurately simulated against SPICE, but in less code. You can check the paper for this, but our pulse machines are formalized according to an operational semantics that keeps track of all this extra timing information, and we sort of accurately or very precisely specify how pulses are propagated. It was really fun to do, but when we were doing it, we realized that we had ended up in this sort of thing called timed automata. So if you're at all familiar with model checking, this would have come up. Timed automata are effectively like Mealy machines, but with timing information on the edges. So you add clocks that can be reset to all of your edges, and so now your edge can be guarded and say something like, well, don't take this edge until a certain amount of time has passed. But this is a well-studied topic. I mean, you can model check it efficiently. So what we did after we had formalized it was, well, we can actually sort of formally compile this to timed automata. So in this diagram, we take a pulse machine, and what we ended up doing was compiling that into 2 separate timed automata. One that represents the output behavior that propagates pulses, which lives in parallel with another timed automaton that keeps track of the internal logic of it. So that's, timed automata are closed under parallel composition, so one very large pulse machine can be made into an even larger timed automaton, but that can be model checked. So that's cool. And so if you're not familiar, Opal is a model checker for timed automata. It comes out of the universities of Uppsala and Aalborg in Sweden and Denmark. So it gives you a temporal logic to query a timed automaton. So what we did, I mean, we think we're the first to use timed automata-based model checking to check the correctness of superconducting, which is totally sweet. But an example of that would be on the top left here. We have this idea of a correctness property that we want to be true of our circuit. And like I said, timing is really important. So this sort of query just says for a certain element, let's say the min-max, if I've reached the end, then certain things needed to happen at exactly the right time based on these delays and propagation delays. So this query specifies that it's always the case that that will suss out. And you might have seen in the previous diagram, we include error states in our automaton. This makes it easy to check that we don't end up someplace we don't want to be. So we can also check these negative type queries. The important things in this big table to look at are these two columns in the Opal section for time and states. For our basic cell library, it took less than a second to verify these correctness properties, which is cool. And in terms of this number of states and the resulting timed automaton, it's on average less than 60, which is also great. But it wouldn't be model checking if I didn't have to mention state explosion. So for even small-ish designs, like an 8-bit bitonic sorter, it becomes very non-trivial to model check this query. I mean, we reached timeouts very quickly. So definitely scaling this up is an active issue that we'd like to pay attention to. It's kind of a grainy picture, but the Opal model checker would give us this sort of timed automaton for a simple gate element. So the key takeaways, I mean, we can sort of live as we do right now at this Joseph's injunction level. We can live with the schematics, but ultimately that produces a cell library. So what we said was, well, we're going to take a behavioral abstraction of these cell elements. We're going to live up here in this green box. So we can either give you some cells or let you write your own. These can be composed into larger designs, simulated and verified, and ultimately maybe fabbed out into a chip. And then furthermore, it can be model checked for correctness. In terms of future and ongoing work, definitely the scalability problem I mentioned is something we care about. But moreover, we'd like to do things like program transformations. So given a superconducting circuit, there's presumably, or very possibly, one that is equivalent but simpler or requires fewer gates. And that's definitely something we care about. So being able to optimize our programs or perform these program transformations, and then of course prove them correct. And that leads into this alternative models to automata option. Automata can be very difficult to reason about as a human. They become big very fast. And so it'd be nice to have a more algebraic model. So we're currently working on algebraic models of these asynchronous systems. And so definitely if you think that's interesting or you care about things like bisimulation, then I'd love to talk. And then finally, adoption. We'd love to see people sort of use this to make designs. Thank you. If you have any questions, I can try to answer them.
Thank you for the very interesting talk. We will now take questions.
Hi, great talk, thanks. I have a question that have you tried to apply your method to actual pulse generated for example, the open pulse for IBM, Qiskit, some kind of thing?
The open pulse, what?
I mean the Qiskit pulse or open pulse, I don't actually know how IBM names their toolkits.
Yeah, if it's something from IBM, then no, we haven't. In terms of, are you just asking, have we made larger designs based on these, or is that a benchmark suite?
Yeah, the design is kind of similar. I just want to understand if you have tried to actually generate the pulse sequence for their machine.
No, the paper has more examples of sort of matching pulse sequences to make sure we've done things correctly, but that could be future work to look at.
Thank you.
Great work, thank you. I was wondering if representing these superconducting programs as discrete state machines is missing anything about the analog noise characteristics of the underlying hardware.
Yeah, great question. Definitely something that we have to think about. As this first approximation, we've considered a discrete time model, but I mean, definitely these sort of quantum effects occur in a continuous time domain, and so that's something that we need to think about modeling. That's also a way to sort of think about moving from the automata space. A lot of model checking for timed automata is based on a temporal abstraction where you almost discretize time again. And so that'd be interesting, something to talk about.
For sure, thank you.
So could you give us an idea of how many people, or what are the teams who will use this kind of DSL, and what kind of traction do you expect for this kind of thing?
Yeah, so we've got some people in the hardware groups at our university that are looking to do accelerator designs. So for instance, like neural network type programming, they want to make faster. And I mean, this is a very unique computational domain where timing is easy. And so if you can make things that care about length of time, well, then you almost get it for free by just passing pulses around. And so I know that like race trees and certain decision tree type like machine learning algorithms, the hardware department really wanted to implement in this. And it was hard, and only a few people knew how to use Spice, and so this kind of grew out of that. Sure.
Other questions? Okay, I have a question. So this is in some sense an analog computation, right? So you have to somehow move from the digital domain to the analog domain. Can you speak to some of the overheads associated with that?
Yeah, I mean, are you saying when we move to a fabbed out design, for instance?
No, for example, like if you want to use this, for example, as a computational kernel, you have to turn your bits into magnetic pulses, right? So, I mean, how do you propose you integrate this with a larger system, for example, if you wanted to use it for acceleration?
Yeah, that's a great question. I know that we have this abstraction that is a discrete model, and that is built on some hardware, or this infrastructure we've already built that can sort of map out to Verilog. And so I think that maybe isn't something I'm as familiar with when you sort of move to the analog aspect of this, but yeah.
Okay, thank you. And I think that's, and I suppose, what do you envision to be the killer app, I guess, like to use annoying startup terminology?
Yeah, that's a great question. I could offer my own example of medical devices, maybe, sort of like heart defibrillators or things that need to be there that should be low power. You don't ever want those to, you don't ever want to worry about changing batteries. But I know that the really hot topics are definitely machine learning type topics, where you have huge amounts of computation and you just want to save power.
I guess one question related to that is, you know, for a lot of these machine learning models, you need to be able to scale up your hardware fabric to a pretty large size. Right? Are there challenges in terms of fabricating interconnect, for example, that can let you scale up to these problem sizes?
As far as I'm aware, no. And yeah, the interconnects are absolutely one of the strong points of superconducting, like extremely minimal energy efficient interconnects. And so, as far as I'm aware, that doesn't become harder as you scale.
Great, thank you.
Thanks.
Any other questions before we wrap up here? All right. Well, thank you everyone for attending the quantum computing session or the quantum session, and thanks for all the great questions.